Entropy and the evidence for atoms. Starting in the 18th century, physicists derived the concept pressure and temperature based on just the bouncing of atoms. Bernoulli, already in 1738, showed how the pressure and temperature of a gas was related to the kinetic energy of particles. But the real understanding of temperature came with Ludwig Boltzmann, who in the 19th century developed the concept of entropy. He calculated the number of configurations that atoms can have in a material. He showed, for instance, that it is extremely unlikely that all atoms of the air in this room, for instance, bounce by chance to one corner of the room. And this is because there are way more configurations where the atoms are scattered throughout the room. Or in physics terms, the entropy is higher for atoms scattered throughout the room. And therefore, matter, when left alone, spontaneously tends towards maximal entropy, just because there is a higher chance for it to do so. And since materials left alone also tend towards equal temperature, the idea arose that entropy and temperature might be related. And when this was worked out, a consistent theory of temperature and pressure formed, based solely on the impact of endless bouncing atoms, thereby proving the existence of these atoms. So we have a lot to get to. Let's start. Hey, good to see you. This is Stephan, author of In Search of the Sublime. On this World History channel, we'll trace humanity's relentless pursuit of scientific truth, moral excellence and enlightenment. You'll meet anyone from Mesopotamian astronomers and Indian yogis to Greek philosophers and Enlightenment scientists. And you'll meet them firsthand using primary sources, giving you valuable insights that transcend the surface level understanding you get on other channels. So go check it out for yourself. Let's start. In the previous video, we've seen how John Dalton used the atomic theory to explain chemical reactions, using the fact that atoms combine into fixed configurations called molecules. The next line of evidence came not from chemists but from physicists, and more specifically from thermal physics, where physicists set out to understand temperature and pressure based on atomic collisions. The first attempt to understand this came from Daniel Bernoulli, who wrote his Hydrodynamica in 1738. In chapter 10 of this work, we see an image of air particles in a cylinder topped by a movable weight. And because of this weight, the air gets compressed in the cylinder until the pressure exerted by the gas in the cylinder is equal to the pressure exerted by the weight. In this chapter, Bernoulli studied this system, and he showed how the gas particles inside the cylinder could be used to explain the inverse relation between pressure and volume that was discovered experimentally in the 17th century. And this relation isn't difficult to understand. If you compress the air, the volume gets smaller, but the pressure will go up. But Bernoulli now showed how this worked mathematically. Through a calculation, he showed how pressure was also related to the temperature of the gas. And he found that temperature was proportional to the kinetic energy of these gas particles. But unfortunately, this discovery was forgotten. Almost a century later, Waterston, in 1843, independently found the same results, but his work was forgotten as well. And it wasn't until the 1850s when the theory finally got accepted. And let's now go through a modern version of what they found. First of all, experiments with gases in the 17th century had shown the relation between pressure, P, the volume, V, of a gas, the temperature, T, and the number of particles of the gas, N. And this relationship, called the ideal gas law, was later written in a formula of this form. P, the pressure, times V, the volume, is K, which was later called the Boltzmann's constant, times N, the number of particles, times the temperature T. The derivation of this formula, of this ideal gas law, from the impact of particles of the gas is called the kinetic theory of gases. Let's now discuss how it works. We start with Bernoulli's cylinder, and instead of a lot of particles, let's simplify it and imagine just one particle moving up and down the cylinder. Let's now calculate the pressure exerted by this particle as it bounces against the weight at the top. We do this by calculating the average pressure that the weight exerts on the particle as it makes a round trip from the bottom up and then down again. And the pressure, by the way, P, is defined as F over A, the force F divided by the area of that weight, A. Now we'll go through some high school mathematics. And if you can't follow this, no worries, just skip through it, for the conclusions will be quite interesting. The force of the weight, according to Newton's second law, is equal to m times a, where m is the mass and the small a is the acceleration. So the formula becomes m times a divided by capital A. And acceleration is the change in velocity, dv, delta v, divided by the time, delta t. So the formula now becomes m times delta v divided by delta t times a. Now the next step, we fill in the time, which in this case is how long it takes from the atom to make that round trip, and which is equal to the distance traveled divided by the velocity of the particle. Now if the cylinder has length L, then the distance traveled up and down is 2 times L. So delta t, the time, is distance divided by velocity, or 2L divided by v, with v again being the velocity. And if we fill this in for the delta t over here, we end up with P is m times v times delta v divided by 2L capital A. And we can now simplify this a bit if we realize that L, the length, times A, the base of the cylinder, is equal to the volume of that cylinder, for which we use capital V, as you can see here. So here I've written the formula that we ended up with, which we'll now simplify even more. Delta V is defined as the change in velocity of the particle. First the particle moved upward with velocity v, and then downward with velocity minus v. And the difference between plus v and minus v is 2v. So instead of delta v, we can also write 2v, which we've done over here. And because we already had 1v, we now have v squared. And this formula can be further simplified if we cross out those 2 and 2 here. For 2 divided by 2 is 1. And this formula can be simplified even more. For perhaps, if you remember your physics from high school, you remember that mv squared is 2 times the kinetic energy. The formula for the kinetic energy is half mv squared. So mv squared is twice the kinetic energy. If we now take the v to the other side of the equation, we end up with P times v, the pressure times the volume, is equal to 2 times the kinetic energy. And this is a very useful result. For we see now, as promised, that Bernoulli found that the pressure of that gas particle is related to the kinetic energy of that particle. Now, I hope you remember, we looked at just one particle moving up and down. But what if we do this for a lot of particles, say n particles? If we then do the whole thing again, we end up with the same formula, but now with an extra n here. And now the pressure is related to the kinetic energy of all the particles combined. And notice, by the way, I've also added some extra brackets here. And this is because the kinetic energy of all the particles doesn't need to be the same. And this then becomes the average kinetic energy. The bracket simply means the average value of the kinetic energy, in this case, of all those particles. Now we do a little trick. We compare our formula, P times V is 2n times the kinetic energy, with the ideal gas law that was found experimentally in the 17th century. P times V is K times N times T. In both cases, we have P times V on the left side. So if we then combine both formulas and cross out the N, we find that K times T is equal to 2 times the kinetic energy. And if we take that 2 and throw it to the other side, we find that the average kinetic energy is 1/2 times k times t. So now we found another useful result, that the temperature of a gas also has something to do with the kinetic energy of the particles. So the energy of the particles determines both the pressure and the temperature of the gas. And this formula, by the way, the kinetic energy is 1/2 times k times t, is called the equipartition theorem. And it is a very important formula in physics. Now, one more change to get a better result. Up until now, we've only had particles that moved up and down, but particles can also move in this direction or in that direction, or in a combination of those three directions. If we account for that, we have to multiply our formula by 3. So then the kinetic energy becomes 3 divided by 2 times k times t. And notice, by the way, that this formula can be used to find the average velocity of gas molecules, since the kinetic energy is 1/2 times m times v squared, and v is the velocity of the particles. Now, because of the brackets, this gets a little more complicated, as you can see in the note below, but that is more for specialists. Now, beautiful conclusions, but notice for a moment that in the last few steps I've cheated a bit. Because I've set out to derive the ideal gas law, P times V is K times M times T, but what I've done is I've actually used that formula to derive that equipartition theorem. So this wasn't a derivation of the ideal gas law after all. To actually do that, we need the next step, and for that we have to dive into statistical physics. And to understand statistical physics, let's start simple. We start with an example of coin flipping. Suppose we flip a coin 3 times. In that case, there can be 8 possible outcomes. It can be hat, 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 tails, hat, tails, hat, tails, hat, 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 tails, 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 hat, tails, tail, tails, hat, or tails, tails, tails. Those are 8 different outcomes that are equally likely. Well, in statistical physics, these 8 outcomes would be called microstates. But, as you might have noticed, some states have an equal number of heads and an equal number of tails. Take for instance THH, HTH, and HHT. These are 3 different microstates, but they all have 1 tails and 2 heads. And we call these 3 microstates, which end up effectively with the same result, a macrostate. So this particular macrostate contains 3 microstates. And that number of microstate in one macrostate is called the multiplicity, for which we use the symbol omega. Let's apply this for this instance. The multiplicity of 0 heads is 1, because there's only one case with 0 heads, namely TTT. The multiplicity of 1 head is 3, because there are 3 cases with just 1 head. The multiplicity of 2 heads is also 3. And the multiplicity of 3 heads is just 1, that is HHH. And now notice for a moment that the macrostates in the middle are more common. We have 3 of each, while the macrostates on the side, HHH and TTT, are less common. We only have 1 of these. So if you were to bet on a macrostate, you would pick 1 head or 2 heads. Now this effect becomes way stronger with more tosses. Take for instance 100 tosses, the results of which you can see in the graph below. On the horizontal axis you can see the number of heads, and on the vertical axis you can see the number of microstates for that amount of heads. And here you notice that most microstates are centered in the middle, while there's almost nothing at the sides. And now look for a moment at the height of this graph. At its highest we have 1 to the power 29 microstates, and this is just with 100 tosses. If you had to bet on a microstate, you'd better bet around 50 heads. Definitely not like 2 heads or 90 heads. The chances of that happening are close to 0. All your chances are in the middle. Now we can play a similar game for a solid. And let's assume for a moment that a solid consists of a grid of atoms. And those atoms can move in 3 directions, up and down, left and right, forward and backward. And in each direction there's an energy associated with this motion. Let's start for simplicity's sake with just one particle that can move in those three directions. And let's call the unit of energy that a particle might have E. In that case, there's only one microstate where our particle has zero energy in all directions. It has zero energy in this direction, zero in that direction, and zero in that direction. So the units of energy are now 0, 0, 0. There's only one way to do this. So the multiplicity of zero energy is only 1, namely 0, 0, 0. Now let's move to the case where we have one unit of energy. That unit of energy might be in this direction, or in this direction. So we have three different microstates right now. 1, 0, 0, 0, 1, 0, 0, 0, 1. And now let's take two units of energy. We can have two units in this direction, two units in that direction, or two units in that direction. Or we can have one unit in this direction and one unit in the other direction. And if you add up all those possibilities, you can see them there, you end up with 6 different possibilities to distribute that energy over that particle. Now we're going to play the following game. Let's take two of these solids and place them against each other. And we'll call this solid A and this solid B. And we'll assume that those particles can now exchange energy. Similar to if we have one hot block and a colder block and we put them together, the energy of the hot block will move to the cold block until both have the same temperature. And now each unit of energy E can be on either side because it can move from one solid to the other. And let's now for instance take a few thousand particles in solid A and a few thousand in solid B, and then a few thousand units of energy spread out over those two solids. As you can imagine, the number of microstates can become insanely large in this case. For there's so many ways for that energy to divide over all those atoms in those two solids. And as you can imagine from that simple coin tossing experiment, most of the microstates in this example will be very unlikely. So unlikely even if you actually do the calculations, that you would have to spend the time span of the entire universe to have even a small chance of that energy being distributed in some unlikely microstates. For instance, the microstate of all energy being in one particle. That will just never happen. And in real life examples it is even worse. For objects in our surroundings tend to have not a few thousand particles as in our solid example, but roughly 10 to the 23rd particles. And this makes the peak of that graph so high and so thin that our system will move as good as always to the macrostate which has the most microstate, and then it will stay there. For macrostates too far from that peak in the center will be so unlikely that will just never happen, even if you would wait many times the timescale of the entire universe. So we can conclude, systems spontaneously tend to the macrostate with the most microstates, just on the basis of probability alone. And this is called the second law of thermodynamics. And usually, by the way, this law is formulated in terms of entropy, which we'll discuss now. Entropy, for which we use the capital S, is just like our omega, a measure of the multiplicity, which, as I hope you remember, was the number of microstates in one macrostate. But for mathematical reasons that you don't need to understand right now, we take the logarithm of that multiplicity, as you can see here, and we multiply it by the Boltzmann constant Kb. So this here is the entropy, but for our purposes in this lecture, it is enough to assume that the entropy is just somehow a measure of the multiplicity. And with this definition, the second law of thermodynamics simply becomes that entropy tends to maximize, which is still the same conclusion, that a system will tend to its macrostate with the most microstates. Now let's look at a graph for our two solids A and B that are placed together. And let's add 100 units of energy to these blocks. On the horizontal axis, we now see the number of units of energies that are in solid A, and the rest is in solid B. So if we have 0 units of energy in solid A, all 100 of them are in solid B. And if we have 20 units of energy in A, then 80 units of energy are in B. And on the vertical axis we have the entropy, which is related to the multiplicity. The blue line gives the entropy of solid A, the black line gives the entropy of solid B, and the total entropy is just the addition of A and B, which is the red line you see at the top. And according to that second law of thermodynamics, the system will tend to the situation in which that total entropy is maximized, and that is in this case with 40 units of energy in A and 60 in B. And by the way, I made the number of particles in A and B a bit different to make that graph a bit asymmetrical, which will be useful later on. Now, we also know from experience that the system will also tend to a thermal equilibrium. If we have one hot block and a cold block, the energy will move from the hot block into the cold block until both blocks are eventually at the same temperature, and that is called thermal equilibrium. So at thermal equilibrium, the temperature is the same and entropy is maximized. So perhaps Boltzmann thought, these two concepts have something in common. Let's now do some calculating. At the maximum, the total entropy is constant. The graph is horizontal at this point. And from this, we know that the derivative, which is the change of the entropy, must be zero, because on a horizontal line, the entropy doesn't change. And this should mean that the derivative of the entropy of solid A and of solid B must together also be zero, because the entropies should add up. And we can write this mathematically as follows. dSA divided by dEA plus dSB divided by dEA is 0. That is, the derivative of one plus the derivative of the other must together be 0. Well, here I've given the same expression again, and we can luckily simplify it a little bit. Since the energy that is gained by solid B must be lost by solid A, because it then moves from A to B, the gain in energy for A, dEA, must be equal to the loss of energy B, or minus, that is the loss, dEB. So we can exchange dEA by minus dEB, as we've done over here. And because of this minus sign, we can now take that whole term to the other side, giving us dSA divided by dEA is dSB divided by dEB, with now the A's on one side and the B's on the other. Both sides are now completely equal, except for the A and the B. Now we can compare this formula with the temperature equilibrium, which states the temperature of A will eventually become the temperature of B. And if we compare these formulas, we see that the temperature has something to do with the derivative of the entropy, or the slope in that graph. And let's now examine how specifically they are related. Notice that the slope, or the derivative, for a low energy for A is much steeper than at a high energy, as you can see here. So a steep slope corresponds to a low energy, and with low energy we also have low temperature. So as a result, the temperature must be inversely related to the derivative of the entropy. The higher the entropy, the lower that slope is, so the lower the derivative of the entropy is. And we can see this written here. 1 divided by the temperature is equal to the S divided by the E, where a high temperature now gives a low slope. Now that this formula completely checks out, we can check by applying it to the real world. Here, for instance, and I'll skip the derivation, is the formula for the entropy of a monoatomic gas, such as helium for instance, which are just single atoms of helium bouncing around. If we fill in this S in our formula for the temperature, and we take that derivative, we end up with 1 divided by the temperature is 3 times N times K divided by 2E. And if we then juggle some of these variables around, we get E is 3 divided by 2 times N times K times T. And this we've seen before. It was called the equipartition theorem. So we get the correct result that Bernoulli also found in his calculation, which gives us the confidence that our definition of the temperature here is indeed correct, for it gives us the correct result. And this formula can then easily be combined with the formula that Bernoulli had found, and that will give us the ideal gas law. And in this way, we have derived temperature and pressure just from bouncing atoms, which gives us even more confidence that atoms must indeed exist. In the next lecture, we'll give the evidence found by Albert Einstein that finally definitively proved the existence of atoms. But for now, if you want to know more about the history of science or any other topic from world history, then read my book In Search of the Sublime. You can read it completely for free on worldhistorybook.com, or you can buy a physical copy on Amazon. Thank you so much for watching. Bye bye.